In this video, we're going to learn about intermolecular forces, otherwise known as IMFs. So intermolecular forces explain why molecules stick together in the solid and liquid phases. When you think about it, until now we've learned why it is that atoms will chemically bond to one another and form molecules through covalent or ionic bonding or metallic bonding. But we haven't actually discussed how it is that molecules exist and they aren't just floating around freely and separately from each other in the gaseous phase. Why is it that we have liquids? What is causing molecules in the liquid phase to stick together? And same with the solid. Well, IMFs explain that. And when we look at water, for example, a classic example, especially if you've taken biology before, you know that there's hydrogen bonding in water. And specifically, it is hydrogen bonding that occurs between separate water molecules. And so there's an intramolecular covalent bond between oxygen and hydrogen in a water molecule. That is an intramolecular interaction, and it is a polar covalent bond. But because of the great polarity here in this bond, because that oxygen is partially negative, and because the hydrogen in an adjacent molecule is partially positive, there can be attraction between that partial positive and the partial negative in different molecules. And that is called a hydrogen bond. So let's talk about the different types of intermolecular forces. The first is called a dipole-dipole interaction, and they occur between two different polar molecules. So when we consider hydrogen chloride, hydrogen has an electronegativity of 2.1, chlorine has an electronegativity of 3.0, and that difference in electronegativities indicates that you have a polar covalent bond. Now, the overall molecule is polar because there's only one bond, and so the chlorine in one HCl and the hydrogen in another HCl will be attracted to each other. And if you the more polar your covalent bond, the more strong the dipole-dipole interactions will be. So actually, we can talk about hydrogen bonding, which, again, you know about this from biology. This is a very extreme form of dipole-dipole interaction. As I said, if you get really big electronegativity differences, then you're more likely to have a strong interaction, a strong dipole interaction. And that actually comes up when we get to the point of even hydrogen bonding. So when we have water, there will be a donor and acceptor in the sense that there will be one atom that is donating electrons, or rather one atom that is accepting the hydrogen, and then another molecule that is donating the hydrogen. And that's how it works with water. In the case of NH3 and H2O, when they're mixed together, there can also be interactions among the different molecules. So if you've got a whole bunch of water molecules, they may be interacting with one another, as we know from up here, and a bunch of NH3 may be interacting with more NH3, but also in a solution that has both of them, there will be interactions between the NH3 and the H2O. And so the partially positive hydrogen of NH3, for example, may interact with the partial negative on the adjacent water molecule. Additionally, you could have a case where a water molecule is interacting as such. We have the H of one water is attracted to the lone pair on the nitrogen of an NH3. This is possible as well. Now, hydrogen bonding can only happen when there is an extremely polar bond between hydrogen and something else. And the examples are FH, OH, or NH. Whenever you have those bonds, the hydrogen is able to interact with a lone pair from another atom, basically, in a way that has such strength that it would be called a hydrogen bond. Good way to remember this is that hydrogen bonding is FON, F-O-N, F-O-N. So again, you need an NH bond, an OH bond, or an FH bond for hydrogen bonding to occur. All right, so how about nonpolar substances? If you consider oils or plastics, they are very much nonpolar molecules. There's no polarity there at all, and yet they will stay together in the solid or liquid phase. In fact, if you take water and try to boil it, it takes a while to get there, but at 100 degrees Celsius, water will boil. If you heat oil, like olive oil, for example, to the same temperature as 100 degrees for water, you won't see boiling occur. You'll actually see the oil still sticking together, which indicates actually that this nonpolar oil has actually very strong intermolecular forces. And so that might be a bit confusing, since there's no polarity there. But what we can do is, we can consider the last intermolecular interaction that we have to talk about today, which is called London dispersion forces. And every single molecular compound has London dispersion forces, including water. Water is molecular, and you may say that the hydrogen bonding in water is very important. That is true, but water being molecular, it also has some amount of London dispersion forces. They're not as important, but they're there. The strength of the London dispersion forces increases with increasing size of the atom or molecule's electron cloud. Going back to water, we know this is very polar, but we also know that hydrogen has 1 electron, oxygen has 8, so we only have 10 electrons in this molecule. It's not a lot. It's not a lot at all. And so the dispersion forces will be relatively weak, but because of the electronegativity difference, we have a very strong dipole moment. And that's why, again, the hydrogen bonding is more important in water. But in the case of oil is huge. Oils and plastics are enormous molecules. For an oil, you'll have 18 carbon atoms and a whole bunch of hydrogens and a couple of oxygen. The number of electrons total is massive. And so the dispersion forces, kind of the sky is the limit, because if you can just make a bigger and bigger and bigger molecule, even if it's nonpolar, you're going to get stronger and stronger and stronger dispersion forces. And you might be wondering how dispersion forces work. Well, let's consider a helium atom. Helium has 2 electrons, so it's easy to think about, easy to work with. There's a nucleus in the middle, and let's say the electrons are floating around randomly, but if we freeze time at one moment, maybe at this particular moment, the 2 electrons are actually kind of close together. They're moving around fast, they're moving around randomly. Maybe at this particular instant in time, we have the electrons asymmetrically distributed. In that case, we have a partial negative over here on the left side where the electrons are, and a partial positive on the right side where there are no electrons. And so as a result, that's going to cause a nearby helium atom to have its electrons move closer to the positive, the partial positive on the adjacent atom, and that causes an asymmetric distribution, at least for a moment, in that atom. It seems really strange and kind of lame, and in reality, like with helium, for these interactions to really be significant and to get helium to get out of the gaseous phase, you pretty much have to cool it down to absolute zero, which is impossible, but it's very, very close to absolute zero. I want to say the boiling point is like 4 degrees Kelvin. So you've got to cool very close to absolute zero to get helium to stick together. But if we were considering something a lot bigger and harder to draw, with tons and tons of electrons, you could probably imagine that there would be an asymmetric distribution of electrons all the time. You'll never get a perfect distribution of the 54 electrons in xenon. And so there will be slight positive and negative on different parts of a xenon atom all the time. It's just that it's moving with the moving electrons. And so that will cause xenon to be something that will stick together a little bit more easily than, say, helium, which only has 4 electrons. Now, strong IMFs, they correlate with a high boiling point. Think water, very sticky. The molecules stick together. It's very hard to pull them apart from each other. So you got to really, really heat them up to exceed the boiling point. Also, they correlate with a very high surface tension. So what this means is that if you were to press on the water, you wouldn't necessarily break through it. And that's just because the water molecules, they are sticking to each other, and you find it harder to break through that point where they're sticking together. And actually, the water skimmer, the bug, is able to exploit this. It's much lighter than me and you, and it can glide across the water because it's light and it doesn't have enough weight to push between the water molecules. It would not be able to walk on water or glide across water if water didn't have such a great surface tension. Put this bug in some other substance like carbon tetrachloride, which is also a liquid, and it would sink. Additionally, strong IMFs correlate with high viscosity, meaning something that is very resistant to flowing. Water may seem like it's very easy to pour, but it actually is less easy to pour than a lot of liquids like benzene and, as I said before, carbon tetrachloride. Additionally, something that's very viscous would be like molasses, for example, or honey. All these liquid sugars, if you will, these liquids that have a lot of sugar in them, the sugar causes really, really strong, hydrogen bonding, actually, because carbohydrates have a lot of OHs on them. And so as a result, you have very strong IMFs among sugars, and thus high viscosity. And then finally, there's low vapor pressure. When you consider water, water will evaporate, but slowly, very, very slowly. If you were to pour out, say, acetone, nail polish remover, an equal volume of nail polish remover will evaporate much, much, much faster than water. And that's because nail polish remover, acetone, is much less polar and has weaker IMFs than water. Finally, I do want to point out some trends that we have here. Notice that in the case of H2S and H2SE and H2TE, these are the hydrogen chalcogenides. S, Se, and Te are all in the same group. They're all group 6, as is oxygen. So what we see here is that there's an increase in the boiling point of these compounds as you're going down the group. And this can be attributed to the fact that tellurium has a lot more electrons than selenium, and selenium has more electrons than sulfur, all right? And so the dispersion forces as you go down the group are increasing. And those dispersion forces apparently matter quite a bit because you end up with a higher boiling point. Actually, the polarity is higher in hydrogen sulfide than in hydrogen telluride, but apparently that isn't the factor that matters most. Data shows that hydrogen telluride has a stronger IMFs because it has a higher boiling point. The difference, though, here is that water has the highest boiling point of all. It has the weakest dispersion forces because it has such a small electron cloud, but it has hydrogen bonding. The O to H bond is so polar that it creates a really, really strong intermolecular force between the hydrogen of one water molecule and the oxygen of the next. And that's why water has the highest boiling point of all of the hydrogen group 6 ides. You'll notice the same with HF, and as you go down the group to hydrogen chloride, hydrogen bromide, and hydrogen iodide, you'll also notice the same trend with ammonia, which also has hydrogen bonding, versus PH3, ASH3, and SBH3. The last thing, though, to point out is that CH4, there is no hydrogen bonding in CH4. This is not a polar enough bond. And so because there's no hydrogen bonding, all you have are dipole-dipole interactions and dispersion forces. There's very, very low dipole-dipole interactions. I want to say it's 2.5 is the electronegativity of carbon, 2.1 for hydrogen. So the difference is very, very low. And as you go down the group, you may have slightly less polarity, slightly less dipole-dipole interaction going on, or slightly more, depending. But what matters more is the fact that the dispersion forces are going up, apparently. I wouldn't expect you to be able to make this comparison yourselves necessarily, but I would expect you to understand that if you have one compound and another, which is more polar. So I hope this video has helped. Let me know if you have any questions or comments in the comment section below. Thank you.